Good morning and welcome to the NPTEL course Advanced Distribution System Analysis and Operation. We are continuing with our module 7, which is Artificial Intelligence Enabled Control in Distribution Network. In the last class, we have seen that what is AI and what is the scope of AI in distribution network application. Okay. So, today we will see different applications of AI in different domain of the distribution network. So, we will start with AI enabled management of DERs, like the application of AI in the distributed energy resource management. So, what are the possible management you can do with AI for DERs? First thing is that you can do the forecasting process. That means you will predict, let us say for next day or for next month or for next year, what will be the generation from your solar panel or from your wind turbine. So, you can do the solar or wind power generation forecasting. That will help you, that we have seen for the OPF study, that if we know that how much we are generating, that will help us for doing the management properly. The second thing, which is now coming in a very aggressive manner, that is that control of the inverters with the help of AI. Now, why that is needed? That is needed because you know that the control of inverters should be of in a microsecond or millisecond time frame, right. So, that means if your control is not responsive within that time frame, then you will miss the most favorable operation, or maybe it will lead to some erroneous operation. So, in this case your AI is a very fast acting, that we have seen in the features of AI, that it will learn, you have a trained model and you just test it and the testing result will come within a few microsecond or millisecond time. Okay. So, if that is the case, then you can use AI for active and reactive power output regulation from the inverters, that whenever we give that P command or P reference command to the inverter, or from there you will get the V reference and the I reference, that reference can be generated in a very small time frame. Okay. So, you need not to solve the entire OPF, what we used to solve. If you solve a classical OPF, which is a big problem, if you solve it multiple times, you have seen even the real time OPF is taking around 5 minutes time. So, if that is the case, then your time frame you cannot reduce below 5 minutes, right, and that is for 123 bus system. If you go for larger system, let us say you go for 8500 bus system or 10,000 bus system, then this time will be enhanced, right. So, there your AI comes into rescue. So, it will be trained with very large or bulk model and you will get the testing result in a very short time frame. So, that is why we use this active and reactive power output regulation with the help of AI technologies. And the third, you can do the storage and EV management, that is the charging and discharging schedule of the storage, or you can get the G2V or V2G support from the EV, when to do that, when to get the support, when to charge the storage, these decisions. It is same like your battery management or storage management, that you also can do with the AI. So, we will see one by one few examples today's lecture, that how it is done. So, first we will see how you can do the solar power forecasting. Okay. So, integrating solar energy into power grid is difficult due to its unpredictable nature. That we know that solar energy is a very uncertain and intermittent power source, leading to voltage surges, instability and financial losses. So, that means you predicted for some energy for the next day, but actually in the next day is a cloudy day. That means you will get almost zero energy. If that is the case, so you have set your dispatchable generators, that means let us say diesel generators, according to the setting that you will get some power from your solar. But if at the last moment you do not get that power, then what will happen? Either your diesel generator has to ramp up very fast, or your voltage will drop down, or you have to cut down some of the loads from your circuit. So, that will go for financial losses, or else if it is an unscheduled power taken from the synchronous generator, then your frequency will drop obviously. If that happens, then you will lead to instability of your system. So, for that you need a good forecast model which will help and require also to attention like timestamps. It needs forecast horizons, input analysis, data processing, weather classification, network optimization, uncertainty quantification and performance evaluation. So, all this data you need for doing a good prediction of the solar power generation. Like you need that on which day you are trying to predict that solar power generation. Is it a very sunny day in the summer, or it is a very cloudy day in the monsoon, or it is the day in the winter? Which day? What is the time frame when you are trying to doing the forecast? Second, your weather, that means whether it is a cloudy weather or sunny weather or rainy weather, what is the weather, and also how much uncertainty you are getting from that prediction. That means what is the error level of your prediction. We have seen in OPF that we have to model that uncertainty, and for doing that uncertainty, first you have to be sure that your prediction is not 100% accurate. That means how much error is there. It is a 95% accurate or 99% accurate, or it is 60% accurate. First you have to know the error level of your prediction. If that is known, so depending upon that you will fix that what will be the mean value, and that mean value will give you how much will be the tail or the standard deviation for that PDF. And if you get a good standard deviation, then you will see that how much you have to elongate your tail of that PDF function, right. Then artificial neural network, which is normally used for predicting the short term photovoltaic power forecasting. So, ANN is a very powerful tool for forecasting the solar power generation when it is short term forecasting. CNN or convolutional neural network are excellent at capturing deep nonlinear input output characteristics in the model. That means, when you use multiple domain or multidimensional data for predicting a solar power generation, at that time it is better to use the deep learning. So, for in between that CNN is the most promising one. So, you can see also from the diagram that if you know the weather, then if it is a sunny weather you have expected and suddenly a cloud comes, then your generation will fall abruptly. So, your prediction algorithm must be smart enough that it will have a diverse amount of data or diverse situation data that will predict this cloud or your rainy season, uncertain rainy weather. So, which are the factors which you have to consider while doing the solar power forecasting? First, you have to know for which horizon you are forecasting. That means, are you doing it for intra-hour? That means for a very short time frame. Like now it is, if it is at 12 p.m., you are predicting for 12:01 p.m. That means just within a 1 minute time interval. If that is the case, then it is a very short term prediction we say. Second, it is short term. That means when your time frame for prediction is from 30 minutes to 360 minutes, that means 3 hours. From 30 minutes to 3 hour time frame you are doing the prediction. Then you have intraday, that is for 6 hour to 24 hours. That means you are doing the prediction for the, let us say, next day. So, today you are sitting and you want to know how much your solar panel will generate tomorrow. So, if that kind of a forecasting horizon you are choosing, so it is called intraday forecasting of the solar power generation. And then you have a long term one which is greater than 1 day. That means you are predicting for, let us say, 1 week, next week, or you are predicting for, let us say, next month, or for a particular season, that you want to know for summer time how much will be from May to, let us say, August, how much will be the generation from my solar panel. It is a monthly, weekly or yearly. If you are forecasting for that generation, then it is a day ahead generation or long term generation. Okay. Then the second factor which we consider, that is called weather classification. That means where you have to see whether you are doing it for a cloudy day or for a sunny day, Also you have to see whether it is a summer or it's an winter or monsoon. Generally we have these three seasons in our country. So this seasons, which season you are trying to predict, that means this time horizon what you have chosen, it falls under which season. Again, in which season, let us say you are doing for intra hour or intraday, so you have to train your model with which kind of data, cloudy data or a sunny data. So that weather classification you have to choose properly. Then the third thing is that forecast model, that means which kind of AI technology you will choose for the solar prediction. All technology, that means it is not mandatory that you will choose abruptly any AI tool and that will perform good prediction. That may be good in classification, let us say, but that may not be good for time series prediction. So if that is the case, then whether let us say for other application it has 99% accuracy, but if you chose it for the solar power prediction, it give you 50% accuracy. So if this happens, that means your choosing of the forecast model is bad. If that is the case, then you have to choose another and you have to do some trial and error, okay, which will give you a best solution. And the last but not the least, that is the forecast model input, which data you have to choose. Not only model, but you have to see which are the data that is needed highly for good solar power prediction. Okay. Now we will see which data is needed. That means which data has the more dominance when you are going for solar power prediction. First is that ambient temperature you need, solar irradiance you need, relative humidity, total precipitation, snowfall amount, total cloud cover, high cloud cover, medium cloud cover, low cloud cover, wind speed, wind direction, air pressure, module temperature, angle incidence, generated output power and timestamp. So these are the environmental data you need. Other data obviously you have, that is how much is the tilt angle for your solar panel. Okay. So what is the let us say efficiency of your solar panel, which kind of solar panel you are using, it is a polycrystalline or monocrystalline or it is an amorphous, which kind of panel you are using, that you know, because that you when you installed that solar panel you have noted down all these parameters of your PV panel. But what you do not know, that is the weather data, which keeps on varying every day. So this data you can fetch from your meteorological department office. But now you have to see that there are almost, you can see that almost 10 to 15 data is there, right. 10 to 15 data you have from your meteorological office. Now if it is a, let us say you are trying to predict your solar generation, you need a huge training data set. So for this 15 data, if you have got 1 year data, that means it is a 365 data, let us say it is an 1 hour data. So 365 multiplied by 24, so it is 7560, 7000, almost 8000 data set, training data samples you have almost. So if you have, then do you need all those data, like whether you need this generated output power, obviously you need, whether you need angle of incidence, whether you need module temperature, this kind of data whether you need or not, that you will get after evaluating the correlation between the input data and the output data. That means the correlation between your meteorological factor and the your output power generation. So if they are highly correlated, so that data is dominating your solar power generation. So highly correlated data you have to consider for prediction, and if you do not consider it, then you will get very low accuracy in your prediction algorithm. So first you can see that solar irradiance has the highest correlation with the solar power generation, that is almost 0.98 per unit. So correlation coefficient is almost 0.98, that means almost 1. So if you have no other data and if you give only solar irradiance, you will also get your accuracy of the prediction that will be more than 90% or let us say 80%. Next is the temperature, that has almost correlation coefficient of 0.76. So these two data are the most dominating data for your solar power generation. So, if you want to predict solar power, you have to consider solar irradiance and temperature as an input data. Other data you can see, they are not that much significant. Obviously, precipitation has little bit of higher correlation, but cloud type, relative humidity, wind speed, air pressure, these are not required, not much required. These are all redundant data. If you feed them, this will be a redundant data, and sometimes they lead to a lower accuracy model. Okay. So, with this, after getting your data, then what is the next process? You will get data from your meteorological office. So, that data will not be a perfect, because data collection process is not perfect. That will have some missing data, some erroneous data, some bad data. So, how to process that? So, before feeding it to the AI model, first you have to do some pre-processing. So, accurate forecasting heavily relies on high quality input data, including historical PV output, meteorological information and geographical details. Okay. So, all this data you have to feed, but that is to be a very high quality. That means, you have to rely, or you have to trust that whatever data you are feeding, that is at least 100% accurate, no error in that data. Okay. So, data set often contain outliers like spikes, static elements or missing value caused by the weather, demand fluctuation or sensor errors, which can distort the forecast. Okay. So, you are collecting the data from some sensors, right? You have temperature sensors, you have irradiance measurement sensors, or for demand also, let us say you are sensing that how much power or voltage or current it is generating from the solar panel. So, all this data you are collecting through a measurement equipment, and in no measurement unit it will give you 100% accuracy. It always have some error in that measurement process. So, if that is there, so you will see that sometime the clock is not properly set. So, it will miss a certain time step. So, there you will see that no data is present, or sometime let us say a sudden spike has come that is of no use, but it has recorded it. So, if this kind of things happens, then you have to see and cleanse your data set. So, it is essential to pre-process and cleanse data through methods like decomposition, interpolation or seasonal adjustment to ensure reliability and the accuracy. Negative or missing solar radiation and PV output values, often due to sensor offsets or inverter failures, should be set to 0 for consistency. That means, let us say if you have a solar power generation and it is showing that you are generating minus 5 kilowatt, it is never ever possible from a solar panel. Active power cannot be negative for solar panel. So, that means something wrong happened with the inverter, or something wrong happened with the data collection process. If that is the case, then you have to replace that minus 5 kilowatt with the 0 value, because you do not know how much is the positive value. So, the good thing is that you just keep it at the lower minimum, and that is your 0. Okay. Missing data during peak hours caused by sensor malfunctions or network issues should be excluded from the analysis to maintain model accuracy. That means, by looking at the solar power generation or the peak power generation time, let us say it is 1 p.m. of a very summer sunny day, 1 p.m. So, at that time if you see it is minus 5 kilowatt, you cannot set it to 0, because then that is an error, that will error data, wrong data entry, because at the noon time or also in the sunny day your solar power generation cannot be 0. Okay. So, that kind of data you have to eliminate to avoid the chance of wrong prediction process. Okay. Then the last thing is that you know that we have seen all this data, their unit is different, their range is different. Okay. So, dealing with a very huge range or different ranges of different data is difficult. So, it is better to normalize them, okay. Normalize them in the range of 0 to 1, depending upon their maximum, minimum and the average value. Considering that, you normalize them, and then that will help to preserve input relationships, speeds up your computation and ensure faster convergence of the neural network. Okay. So, we will see an example of how to do the short-term solar power prediction using ANN based models like artificial neural network. So, here the data is collected for every 15 minutes time for one sunny day, and this 4 data has been collected, that is the solar irradiation, ambient temperature, wind velocity and the module temperature. This 4 has been collected. So, you see, if you see, the solar irradiance means the highest correlation data, then temperature the next one, then you have your wind velocity and you have your module temperature. So, these 2 data are essential. Other than that, you can take any other data that may add value or may not add value. Okay. So, this is the your ANN model where only one hidden layer is used. You have your input layer which has 4 neurons or 4 nodes, and in the hidden layer, that is only one hidden layer with 10 neurons to predict the solar power output. At the output layer, you have only one neuron. So, this is your solar irradiation data, this is your ambient temperature wind velocity data, this is your ambient temperature data, and this is your module temperature data. So, this is your input data and this is your model. With that, the training hyperparameters are set. We know what is hyperparameter, we have discussed in the last class. So, number of epochs is 250 maximum epoch. The tolerance, that means the error tolerance is 1 e to the power minus 3. Your learning rate is set to 0.003 and the momentum factor is set to 0.1. So, by doing that, if you do the prediction for the solar power generation versus time, you see that the prediction is almost same and coincides with the actual data. That means your prediction is good and your root mean square error is 0.1. So, that is quite low root mean square error, and you see that with that epoch, with the increasing epoch, your training process is converging. That means it is reaching at the lowest level and being there. Okay. So, that means the ANN model is good solar power forecasting. Okay. So, now we will see after the forecasting what you will do. You have to control the inverters that you will get the active and reactive power output properly from your PV inverter. So, the first application of the AI in the smart inverter, that is the maximum power point tracking. How we are doing it? Neural networks or fuzzy logic controllers can learn the nonlinear relationship between sunlight, temperature, voltage and current. That we have just seen, that you can use neural networks or you can use fuzzy logic as well. You will set the membership functions and their range to learn that what is the relation between your input parameter, the meteorological parameters and your output. So, depending upon that, what will be the power output you will get, that power output you will say that reference power you will set as your maximum power point, and you will instruct your inverter to track that maximum power point at each and every time interval. So, they can predict the best operating point even under dynamic conditions like passing clouds or partial shading. Okay. Then reinforcement learning techniques allow the inverter to continuously self-learn optimal control actions over time, improving MPPT efficiency without needing pre-programmed rules. So, without the supervised learning, if you use reinforcement learning, then what will happen? It will learn on its own, it learns from the circumstances, it learns from its neighbors. So, what is happening that for any changes, if there are any sudden changes is happening, then reinforcement learning need not to have that wide data set. It can learn from its past experience or from its past decision that whether it is going to add a reward or it is going to add a penalty, and if it is a maximum reward is there, then it will follow that process. Okay, and that will improve your MPPT tracking. Now, the second application is the grid support and stability using the artificial intelligence technique. AI models can predict voltage or frequency changes based on current grid conditions and adjust inverter output preemptively. Okay, that means it can just sense the voltage and the frequency. If you give that input to the learned module, and it has already learned with diverse amount of data and the situations of the grid, then it can easily detect whether your grid is under stress condition or it is under healthy condition, or it is completely in the blackout condition. And under that condition, how your D or inverter should behave. That means whether it will run in a grid following mode, or it will run in a volt-var control mode, or it will run in a constant voltage mode, or it will go for a grid forming mode. So, or it should island itself from the circuit and run as a grid forming mode, that means in an islanding condition. So, that grid support or stability that you will get from easily, you can get that decision from the AI. So, AI optimizes reactive power injection to smooth out the voltage spikes and the sags. So, if you see the PCC voltage is dropping down because you have some disturbance in the upper grid. So, by sensing that, if the DER inverters can supply enough amount of reactive power, so that power, if you feed it from the inverter, then the voltage will be boost up. So, that decision, reactive power injection decision, will be taken by the AI very easily. Then AI agents can decide when to prioritize self consumption, storage charging, or grid support based on the both economic and stability factors. Okay? So, we will see another example of centralized reactive power control of the solar inverters. How we can control the reactive power output, just what I said, if you mean sensing the PCC voltage, how the reactive power support you can give from your PV inverters and in a regulated manner. So, the objective is that control reactive power dispatch from your PV inverters by following the IEEE 1547-2018 standard. And what is that standard said? We have already seen that is like on the Q max. Okay? Like if your P is less than equals to 0.2 of your S, then your Q max will be root over of S square minus P square. And if that is greater than of your 0.2 S, then you cannot give your Q max, that will be 44% of your S, that you have studied in our module 2, right. So, that standard you have to follow whenever you will go for reactive power support from the going to give reactive power support from your PV inverters. To reduce the network loss and voltage deviation in the circuit by leveraging or learning the volt-var control using reinforcement learning. So, you are using RL with integrated with the volt-var control that your P to get the reactive power support. So, the problem is that the optimization problem has been framed that it will minimize your total voltage deviation, total loss of the network, and total Q support or Q PV violation. That means that will give you what is your actual Q, and as per your volt-var control what needs to be the scheduled Q, difference of this two. If that means you are violating something. Okay. So, if there is any violation as per the standard and as per your volt-var control mechanism, so that will be minimized by doing this optimization problem. Subject to the constraints that active and reactive power balance, obviously line flow and bus voltage limit, Q limit of the PV inverters using volt-var control by following the IEEE standard. Okay, this is the overall schematic of the learning process. That you have your electric power grid or the distribution grid in a simulator, then you take the input data or the outputs, you sense this voltage, you sense the loss, you sense how much reactive power support you are giving, you sense those things and give it to a deep reinforcement learning agent. And that learning agent will learn that whether my previous decision is giving the grid in a stable and a good economic condition or not. If that is given, then it will generate that okay, it is an reward point. But if it is not, then it will generate a penalty point. Okay? And that action, depending upon that, a new action has been decided, and that will be again fed to the grid simulator or the distribution grid simulator, where you are emulating the response of the grid. So, that is how you can implement offline your reinforcement learning control algorithm. So, for that Markov decision process is adopted generally to learn where a reward will be assigned for each good step, and the central controller has the role to find the optimal dispatch by maximizing the expected value of the discounted reward over a given time horizon. Okay, that is the main fundamental of the reinforcement learning, that for each good step it will reward point, and the central controller will see that which path or which strategy if I follow, I will get the maximum amount of reward from the learning algorithm. That will is your most optimal way to control your PV inverter. So, the model is trained to learn the Q star value, that is the maximum possible expected cumulative reward achievable from state S and action A. Okay, that is your Q star expression if the agent always acts optimally after that. Okay. So, this will give you that for each and every input the total summation of your reward point, and that will give you the best optimal policy. So, if your Q star value is reduced for total time period from t equals to 0 to infinity, is a real time process. So, for t equals 0 to infinity, if you sum all the reward point for a certain state and a certain action, then for an initial state or initial action also you have to define. Considering all those things, you have to determine the most optimal policy, and that optimal policy will has to give you the maximum value of the Q star. Okay. So, what are the observed states? That means we are saying that we will see the states from the grid. Okay. So, what states will observe? First thing is that how many DERs are present in your network. You are a central controller, you are managing the resources in your network. So, first you have to know how many DERs you have. So, how many controls you have to decide it, right. Then what are the PCC voltage of them, because you want to see the voltage deviation. So, you have to know how much is the PCC voltage, that you will measure. Then active and reactive and apparent power from the DER. So, how with your control decisions, how much active, reactive and apparent power you are getting from your inverters. Then DER limit as per the IEEE standard. Okay. By looking at that P, you have to now see how much will be your Q max, right, as per your IEEE standard. So, those things you will note down as an observed state. Then the action, what you will take an action by looking at the states. First, a custom action space is created using 1D vectors containing PV system IDs and an action selection vector for reactive power set point adjustment. That means, you will have a vector of actions. You will say that whether if these states are there, I can take this bunch of actions are feasible or possible for the PV inverters. It may be 10, 20, 50, 100 depending upon the scenario. So, that you have to note down for each and every PV system ID. That means, DER1 you have 10 possible cases, for DER2 you have 10 possible cases. These things you will note down as a 1D vector. Then at each time step the agent selects an action that adjusts the reactive power, okay, based on the observed PCC voltage deviation and the inverter's current reactive set point. Okay. Then by looking at the voltage V, you will see the QV droop characteristics and where that voltage lies, like it is in V1, between V1 and V2 or V2 or V3 or V3 or V4 or V4 V5 or V5 V6, in which range your voltage data falls. Depending upon that, you will decide that what will be your Q value. We have seen the QV droop characteristics, right. So, that Q adjustment value you will decide. Okay. Then the reactive power adjustment is modulated by the VVC droop curve and the IEEE standard, and then you will see what is the value of Q max, and if it is hitting the Q max value, let us say your voltage is under falls under your V1 and V2 category, V1 to V2 category, this category. If that falls, then you have to supply a maximum amount of Q. If that is the case, then you have to see what IEEE standard says in the current situation, depending upon the P and the rating of the inverter, what will be the maximum Q you can support. Okay. then the design encourages the agent to make small conservative adjustments when the local grid is stable, improving control sensitivity and the system health. So, whenever you will see that okay, I am good with all the standards, I am good with all the considerations, but my system is also stable. So, at that time, to make the decision more economic, sometimes you take a very stable decision, but that may not be a very economic decision. So, small perturbation is possible in that decision, and that is done by the reinforcement learning to enhance your reward point value. Okay. So, if that is done, but you have to remember that adjustment should not violate your standard constraint, that should not violate your QB droop constraint, or that should not violate your stability constraint. That is only done when everything is preserved and you are just adjusting for the sake of economic benefit. Okay. So, after that the reward function you have to design. So, a multi-objective reward function with negative penalties, obviously if your penalty is negative, that means you are getting reward, is used to train the agent, focusing on minimizing voltage deviation. That is the first element, that you will see that how much your voltage is deviated from 1 per unit, that is your nominal value. How much you are incurring the loss. So, more losses means more penalties. So, negative of the penalties means you are getting reward. So, and preventing IEEE 1547 violation through reactive power constraint. So, it will see that how much you are violating, if with your current decision, how much you are violating your IEEE standard. Okay. The objective is to maximize the cumulative reward while satisfying the operational constraints, encouraging learning within safe system boundaries. Okay, that is how you will learn your, you will make learn your reinforcement learning. So, this is the case study results with IEEE 123 bus test system. You have PV system at this points and you have single phase PV system at this points. So, you have more single phase PVs and only 2 3 phase PVs. Okay. So, with the learning rate you have first varied the learning rate, because that is your hyperparameter, and you will see which learning rate will give you the highest value of reward, that means least value of penalty. So, it has seen that if the learning rate is very low, that means 0.40000001, you will see your penalty is minus 200, but with higher learning rate you have penalty more. With 0.0001 you have, it is almost minus 400, and with 0.405 you have, it is almost 350. So, these are more. So, your this is the most optimal decision. Okay. So, then highest cumulative reward is minus 200. So, you have to fix your learning rate to 0.0001, okay, 401. So, after that we will see whether your bus PV and the control bus PV inverter control active and reactive power and corresponding the voltage of a particular bus is good or not, that means is following the characteristics or not. So, we can see for this case for bus number 47 that it is your voltage is first, it is at the lowest, that means it is at below 0.1, below 1 per unit. So, this is your 1 per unit graph. So, previously your voltage is 1 per unit. So, after that when that is the case, you are giving maximum reactive power from your PV inverter. After that when your active reactive voltage profile is increasing, that means you are getting good voltage at the PCC, then your reactive power support is also decreasing, right, or you are giving less reactive power when your voltage is improving. And even when your voltage is crossing a certain 0.11 per unit, let us say, so after 0.99 per unit, so after that you started consuming, that means your PV inverter started consuming reactive power to avoid over voltage condition at the PCC. So, that means by looking at the voltage condition, the mode of your PV inverter is changing by following the QV droop characteristics. First, when the voltage was lower, it is at the sending mode. When the voltage is higher, at that time it is in absorbing mode. Okay, and depending upon that your PV is almost constant, that depends upon your weather. Okay, so that means your reactive power then gradually transition to the injecting of the reactive power over time. Okay, and maintaining a steady power output. Okay, so first you will have absorption, then you will have supply. So both the things are possible. You will get power from it when your voltage is low, and you will give power when your voltage is high. Okay. So AI enabled battery operation, you will get forecasting and optimization. AI models like deep learning predict future energy generation and consumption patterns. This prediction help optimize when the charge or the discharge batteries, improving overall system efficiency and reducing reliance on the grid. Real time control and decision making, that is you can do with the battery operation. Reinforcement learning agent continuously learn from the environment, energy prices and demand spikes, and make the dynamic charging and discharging decisions. Okay. AI algorithm react instantly to changing grid conditions, improving the energy balance and system reliability. Health monitoring also you can do, and lifetime prediction with the help of AI. Machine learning models analyze the battery data and see how much life you have for your battery, or you can extend life for your battery or not. Okay. Then you can do energy cost reduction, that means AI forecast electricity price trends and schedule your battery charging and discharging. When you are experiencing lower price, at that time it will charge, it will command the battery to charge, and when you have peak price time it will command the battery to discharge. So that is how you can get a minimized energy cost condition. So integration of the renewable energy with the smart grid, that is also possible, that we have seen when you can predict proper uncertainty or intermittency in the solar power generation, then you can control also their intermittency with the help of battery. Electric vehicle management also you can do. First thing is that you can use random forest, ANN, CNN, RNN and LSTM to forecast EV charging demand. That means in a city how much EV is going to come for the next 2-3 years or 5 years timeline. Load and electricity prices to improve the charging scheduling. AI models like neural networks and reinforcement learnings are preferred over conventional optimization methods for EV charging scheduling, because they handle complex nonlinear and the stochastic problem efficiently. Okay? Then AI helps to manage vehicle to grid system as well, like how much support you have to take depending upon what is the SOC condition of your electric vehicle, and what is the arrival time and departure time after your EV. How is your customer very critical, or your customer is a very flexible type? So depending upon all these scenarios, all this input data, it can says that how much V2G support you can take from the electric vehicle. And if you take that also, how much effect that will give on your battery health, and it will choose only those patterns, or it will choose only those control strategies which will impact minimum impact on its the battery health. Then also with the electric vehicle fleets, you can apply AI to optimize the routes, like and which route you have to travel, that you will get less traffic. Charging schedule and energy usage by considering factors like traffic, battery state of charge and charging station availability in the city. So with the help of AI technique, you can manage the electric vehicle operation, and also you can manage the operation of a charging station. So with this, I end today's lecture on the application of AI with the DERs, and in the next lecture we will continue that how AI can be used for the management of the distribution networks. Okay, thank you.